Hey, if you are new here, this is Chandan and you are watching the learning field. Okay, so in this video or in this lecture, we are going to discuss about the inner product space. Okay, a small discussion on inner product space. Okay, a to the point discussion on inner product space. So inner product space is a very important topic for any higher mathematics exams like CSIR NET GATE and so on. So in this video, we just discuss the inner product space point by point. Okay, so this is not a brief discussion, this is a light discussion or a to the point discussion. Okay, so let's start, and before starting I am requesting you to all those who are new, those who are not watching the previous videos of my channel, and those who are not watching me previously, so please like the video, comment if you have any doubt in the comment section below, and obviously subscribe the channel. Okay, so let's start. So first we comes to the definition of inner product. Okay, so what is the definition of what is inner product? Okay, so let V be a vector space over the field F, that is R or C, and inner product is a map, that is this is the defined two dot and dot, just this is a notation. Okay, so this is a function from B cross B to F such that it satisfies the following properties. Okay, the properties number one is alpha of U plus beta of V in comma W, this is equal to alpha into UW plus beta VW. Okay, where alpha beta belongs to the field F and UVW belongs to the vector space D. Okay, so next the second property is UV equal to BU complement. Okay, so this is since this is a general vector, that is the vector maybe belongs to the complex number C, so that's why we take here the complex conjugate. Okay, so UV this is equal to VU complex conjugate, and number 3 is UU greater equal to 0 and equal to 0 even only if U equal to 0. Okay, so if a function B cross B to F satisfies these following three properties, then a vector space B together with this inner product on it is called the inner product space or IPS. Okay, inner product space. Okay, so now comes to an important remark. The remark is one, if F equal to R, then the real inner product space and the function of inner product satisfies the following dot product. Okay, so that means what? That means if the field is R, then we mean the dot product same as the inner product. Okay, and if F equal to C, then it is complex inner product space or unitary space. Okay, so let us take the examples. So the example one is what? Let V equal to F power n be a F to the power n, that is F tuple n tuple of the space be a vector space over the field F equal to R or C, then the inner product is defined by UV equal to V dagger into U. This is the complex. Okay, so that means we already know that V theta equal to V theta Vt then transpose. Okay, so the V theta V transpose and then the complex conjugate. Okay, so this is the defined, and in real this is simply V transpose. Okay, this is simply V transpose U. Okay, so for all UV belongs to n tuple of the field F. Okay, so then V is an inner product space with the above inner product. Okay, this is the standard inner product on V. Okay, so this is the example of standard inner product on V. The space is where the space is this field. Okay, now number 2 is in the matrix field the inner product is defined by A into B, inner product of AB, this is equal to trace of B theta A. Okay, in this is the general in the space complex space. Okay, in the real space this is equal to trace of B transpose A simply. Okay, and this is the matrix inner product, and for the case of functions, let's V equal to C0, and that is the differentiable functions over the continuously differentiable functions or smooth function over the interval 0 1. Define the inner product by inner product of Fg, this is equal to integration 0 to F Ft into Gt bar into Dt. Okay, this is the complex conjugate of the function Gt. Okay, so now these are the examples of the inner product. Now we comes to a important definition, which is the norm of a vector. So what is the norm of a vector? Let B be an inner product space. Let B belongs to B. Then the norm of the vector B is defined by norm of B. This is equal to root under inner product of B and B for all V belongs to capital B. Okay, so norm means the length of the vector, length or of a vector. Okay, so length of a vector. For example, let V equal to R2 is the vector space over the field R. let the vector x, this is equal to xy, okay, belongs to R2, then norm of the vector x, this is equal to a root under of x into y, okay. So this is equal to simply root under x square plus y square. We all know the length of the vector formula, okay. So this is simply the formula of length of a vector, okay. Now let us comes to an theorem. So this is the formula, okay. Now let us comes to an theorem. The theorem is, let V be an inner product space, okay. Let just a minute. Let V be an inner product space over F and norm be equal to root under inner product of B and B for all B belongs to B. Then number 1 is norm B is greater than 0 for all B belongs to B. Number 2 is norm B is equal to 0 even only B equal to 0, and norm of alpha B equal to mod alpha norm B for all alpha belongs to B and the alpha is the member of a field, okay. And number 4 is norm of U plus B is equal to norm U plus norm B. This is the triangle inequality, you all know that. So inner product space over F, then this is the theorem, that is I think so this is the theorem, okay, that is this is the inner product space and this is the theorem in norm space, okay. After defined norm, then we comes to this theorem, okay. That means what? That means an inner product space is a norm space also, okay. Let us comes to that point, okay. So norm vector space, this is the norm, okay, defined norm. Norm vector space, what is the norm vector space? Let V be a vector over F and a norm is defined is a real valued function defined on this which satisfies this, okay, these 4 above properties, then V is norm is called the norm vector space, okay. So these 4 properties are very important for the case of norm of a vector, okay. Satisfies for norm of a vector, satisfies norm, satisfies these 4 properties, okay. This is the theorem. And for example, let V equal to R2 over R, then norm of xy, this is equal to x plus y. This is a simple example of a norm of a vector space, okay. Now an important remark is every inner product space is a norm vector space, okay, norm vector space. That means inner product space implies what? IPS implies NVS. Just a minute. An inner product space implies a norm vector space, okay. So let us comes to an example. Let B equal to Rn over R, then norm be equal to norm of x1 x2 dot dot xn. This is equal to the defined by max of mod I, then V and norm with this norm is norm vector space, but the above norm cannot obtain from any inner product space. That is, this is the example, that is IPS implies NBS, that is inner product space implies inner product space means norm vector space, but norm vector space means does not imply the inner product space. This is the example for that, okay. Now it comes to parallelogram law. What is parallelogram law? Let V norm with a norm be a norm vector space, then norm of U plus V whole square, this is plus norm of U minus V whole square, this is equal to 2 into norm of U square plus norm of V square. Here an important note is, if V norm V with the inner product is an inner product space with then V satisfies the parallelogram law, okay. That means if V is an inner product, V with an inner product is an inner product space, then it satisfies the parallelogram law, okay. So let us comes to an theorem. The theorem is, let V be a norm vector space, then the define d of uv, this is equal to norm of u minus v, satisfies d of uv greater equal to 0 and d of uv equal to 0 if and only if u equal to b. Number b is d of uv equal to d of vu. Number c is d of ub, this is equal to d of uw and d of wb. That is, if we take any vector in between u and v, then this satisfies the linearity or less equal to type or triangle inequality properties, okay. So this PD becomes an matrix when this is the three properties, main properties of matrix, we all know that. Therefore a norm vector space is also a matrix space. That means an inner product space, this implies norm vector space, this implies also a matrix space, okay. That means we note, the note is, if B is an inner product space, then B is a norm vector space, which is further implies the B is an matrix space. So this is very important statement, okay. You can remind this statement for the further and for future response. Okay, so inner product space is the inner, that is inner product space. Then that means, see from this picture, remind this picture, inner product space implies non-vector space implies metric space, but metric space does not implies non-vector space, or metric space does not implies inner product space. Okay, we also take the examples above, that is for the case of NBS does not implies IPS. Okay, so this we can take the example and other examples also. Okay, now let us comes to an important inequality, which is Cauchy-Schwarz inequality. This is very important inequality. Let B be an inner product space over F, then for the following, for every UB belongs to B, mod of the inner product U and V, this is less equal to norm of U into norm of B. Okay, and equality holds even only if UV are linearly dependent. Okay, so this is very important inequality. Okay, now let us comes to an important concept, which is orthogonality. So this concept is also very important. So let B be an inner product space, then two vectors U and B is said to be orthogonal if and only if their dot product, that is the inner product of U and B, is equal to 0. And we also know that in simple linear algebra, if the dot product of any two vectors is 0, then we say that the two vectors are orthogonal to themselves. Okay, so the similar concept in the inner product space also. Okay, so this implies V equal to 0. So U is orthogonal to V. This is if and only V is orthogonal to U. That means the vectors in the simple vector space, orthogonal means what? The vector is perpendicular to another vector, and the other vector is also perpendicular to the rest of vectors. So there is the same concept. Okay, in just we change the space. Okay, this is not the vector space, this is an inner product space. Now let us comes to the another definition, orthogonal complement. Okay, let B be an inner product space over F if S be the subset of V, then an orthogonal complement of S is denoted by S perpendicular. Okay, and is defined by S perpendicular, this is equal to U belongs to V, such that the inner product of U and V equal to 0 for all V belongs to S. Then we say that the set is called a orthogonal complement of the this S set is the vectors contains that vectors which are orthogonal complement with another vector. Okay, and this is the definition. Now let us comes to an theorem. The theorem is, let B be an inner product space over F if S is a subset of B, then an orthogonal complement of S is a subspace of A. This is an result type, you can say. And the next theorem is, let W be a finite dimensional vector space of an inner product space B, then B equal to W and plus, this is what is orthogonal set. Okay, a subset W of B is said to be orthogonal set if for any UV belongs to W, UV, the inner product UV is equal to 0. Okay, so then the set is called orthogonal set where U not equal to B. Now it comes to orthonormal set. What is orthonormal set? A subset W of B is said to be orthonormal set if norm of U equal to 1 for all U belongs to W, and UV norm of UV, that is the dot product of UV and V, this is equal to 0 for all UV belongs to W for U not equal to B. Okay, now a note, important note is every orthogonal set is orthonormal set is orthogonal set, but not conversely. Okay, now Gram-Schmidt's process, we just say the process, we don't go to the details of this process. Okay, because if we go to discuss this process, then this theorem takes a long process and a long time. Okay, so that's why we skip the complete process, we just write it. Okay, so let UN UN U1 U2 UN be the linear independent set of vectors in an inner product space, then there exists a orthogonal set, and if you want, then I also make a separate video for Gram-Schmidt process. Okay, so comment me if you need this. Okay, complete set of vectors v1 v2 vn such that u v u1 u2 ui this is equal to v1 v2 vi for all I, where that means we have given a set of vectors and we have to construct a orthogonal set of vectors or orthonormal set of vectors. Gram-Schmidt process actually doing what? Gram-Schmidt process is actually to construct the set of vectors to a orthogonal or orthonormal set of vectors. Okay, so this is the work for the Gram-Schmidt process. This is the importance of the Gram-Schmidt process. Okay, So V2 equal to U2 minus this one, dot product of U2 V1 by V1 V1 inner product into V1, and the general formula you just remind this line. Okay, so Vn equal to Un minus Un V1 by V1 V1 into V1 and so on, and up to Un Vn minus 1 by Vn minus 1 Vn minus 1 into Vn minus 1. Okay, so this is the general formula to construct the orthogonal vectors. Okay, V1 V2 Vn. And after we getting the orthogonal set of vectors, we just normalize the vectors to get the set of orthonormal set of vectors. Okay, so the orthonormal set of vectors is just we divide the vectors with their norm. Okay, we get the orthonormal set of vectors. Now important result is every finite dimensional linear product space has an orthonormal basis. This is an important theorem or result. If W is a subspace of an inner product space B, then W perpendicular this is equal to W, and the standard basis of Rn is an orthonormal basis. And now we comes to an important part, orthonormal transformation or orthogonal transformation. This is a big part. I just write one or two result and the basic criterion, and just this, since this is a small discussion. Okay, because inner product space is a huge topic. Okay, so we just here discuss to the point to point. Okay, so let V be an inner product space. A linear transformation T from B to B is said to be the orthogonal if Tx Ty this is equal to x into y for all xy belongs to V. Okay, now let us comes to another theorem. Let T from B to B be a linear, then the following are equivalent. T is orthogonal, Tx equal to norm x for all x belongs to B. T takes an orthonormal basis to an orthonormal basis. That means T is also 1 you can say. Okay, now it comes to a very important concept, which is projection of a vector onto a line. This is a very important question, because based on this concept questions comes in CSIR NET also, GATE and TIFR, NBHM, all types of exam in any question paper, or you can say if we see the 5-year question paper or 2 or 3 or 8 question paper, then a question from this section is also comes. Okay, it comes obviously. Okay, so projection of a vector B onto a line through vector A is given by P equal to X equal to A transpose B by A transpose A into A vector. Okay, this A and B are also vector. This is the image you can say. So this is the x-axis and this is the y-axis. This is the y-axis or xy plane you can say, onto a line. Okay, so projection of a vector onto a line formula is this. Okay, so here I take an example and projection matrix. You have to find the projection matrix where is P equal to X equal to this A transpose B by A transpose A into A vector. This is equal to A into A transpose B by A transpose A. This is equal to A transpose by A transpose A into B vector. This is equal to P vector, and this P is equal to A transpose by A transpose A. This is called the projection matrix. Okay, this is very important. Just remind this formula. So let us take the example A vector equal to 1 4 7. Then we have to find the projection matrix. Suppose then the formula is A transpose by A transpose A. Okay, so A transpose equal to this matrix and A transpose A equal to this matrix, and this is the simply 1 by 1, that is a simple element. So this is equal to the matrix this one. Okay, so the projection matrix is this one. Okay, and I think in a question paper, I think in which question paper there is a questions from this, you have to find the trace of the projection matrix. Okay, so the question is very interesting questions. I think it's a CSIR question or another question, but I just forget it. Okay, so you have to find, the question was to find the trace of these matrix, I think. Okay, so this is very important. So you can check and you can recall this and you can see this formula once before you going to the exam hall. Okay, and the result, projection matrix on projection matrix. Projection matrix is always rank 1 matrix. Projection matrix is a symmetric matrix. Projecting of a vector on a second time do not change anything, that is P square equal to P. Okay, projection matrix is a positive definite matrix. Okay, so these two results are very important, symmetric and positive definite. Okay, based on these two concepts or based on these results, the questions comes in CSIR NET. I just take the examples below. Okay, So projection of a vector onto a subspace. Okay, so projection of a vector B onto a subspace spanned by AI, which are the column space of a matrix A, P equal to AX, this is equal to A transpose A inverse A transpose B, and this is equal to PB. Okay, so P equal to this one A transpose A inverse A transpose is the projection matrix. Okay, and here one thing is noted that this matrix A is not necessarily a square matrix. Okay, this may be a what? This may be a rectangular matrix, and most of the cases this is a rectangular matrix. This is a rectangle matrix. Okay, so for that case we don't have the determinant of the matrix. That's why we can't change this one. That means we all know that A B transpose A B whole inverse. This is means what? We write B inverse A inverse, but here we can't write it. Okay, because this is not a square matrix. Okay, this is an important note. Okay, so let us take an example. A equal to this, B equal to this. Okay, so we have to find the projection matrix. Suppose A transpose A inverse A transpose. Okay, so A transpose equal to the this one, A transpose A equal to this one. So this is a 2 by 2 matrix, 3 3 3 5. Okay, just you can check it. Okay, so A transpose A inverse, this is equal to this one is the simple inverse 1 by 6 into this one, and P equal to therefore A transpose A inverse A transpose. Okay, so that means what? That means this A transpose A inverse into A transpose. Okay, so this is simple matrix multiplication, and we get finally what? Get finally 1 by 6 into this is the matrix. Okay, so P matrix, that is projection matrix for a vector, a projection of a vector to a subspace. Okay, this is the projection matrix. Okay, and the formula you have find it. Okay, so P equal to what? The projection matrix, and the P is just here you can check small p, this is equal to capital P, this is projection matrix into B vector, and B vector is, suppose if we take this one is a B vector, then this is the small p matrix. Okay, now let us take the example, and this is the current question from CSIR NET 2022. Okay, the question says that which of the following are inner product space on R2. Okay, so these are the given. Okay, so this is the given. This is a very easy question which comes in CSIR NET 2022. Okay, the two result is needed to solve these questions. Okay, one is what? The projection matrix or the inner product space. The matrix is symmetric and positive definite. Okay, so we just write the matrix corresponding to the given inner product. Okay, so x1 x1 x2 y1 y2, this matrix is symmetric but not positive definite, therefore this is incorrect one. Just we have to check, and up to this, according to this, we just write the matrix and check whether the matrix is symmetric and positive definite or not. If one of these fails, then we say that this is not an inner product. Okay, so we just check it, check those inner product. So this is symmetric and positive definite, B correct option, and see the matrix, this one symmetric and positive definite. And to check positive definite, you just check the principal minors. Okay, and you all know that, I think, the principal minor method to check the positive definite or not. So this is symmetric and positive definite. Okay, so see symmetric matrix, clearly this is a symmetric matrix, and positive definite means 1 by 1 principal minor and this one, and 2 by 2 principal minor means the data of the this is greater than 0 or not. Okay, so if the principal minors are greater than 0, that means the matrix is positive definite matrix. Okay, matrix. Okay, so here B and D options are correct. Okay, this is very simple question, you all have to solve this question. Okay, so there is a question CSIR NET June 29 edition. Let V be a vector space of polynomials in the variable t, okay, of degree at most 2 over R, and inner product B is defined by f and g, this is equal to integration 0 to 1 ft gt dd for fg belongs to B. Let W equal to span of this one, and W perpendicular be the orthogonal complement of W in V, then which of the following conditions satisfies for H belongs to W perpendicular. Okay, so here we have to the question is based on the word to characterize the function H. Okay, so we have to first find, or we have to try to find the function H, and then we can say whether it is even function, whether it is odd function, and it is a real root or not. Okay, and whether it is 0 or not. Okay, so we have to just try to find the function h. Okay, so let us take, since the functions or the polynomials are at most 2 degree, therefore we take a general polynomial of degree 2. Okay, so ht equal to this one, we take the general polynomial. Now it says that what w equal to span of this one, and w belongs to h perpendicular. That means the h, that means what, h and these two vectors f and g are what, orthogonal complement to each other, or orthogonal set of vectors. Okay, and so that means these two inner product goes to 0 and these two inner product goes to 0. Okay, so we just write this is h and this and this. Okay, this inner product goes to 0. Therefore we just apply the method given here, and 0 to 1 into this one, this is equal to 0. Just simple integration. Okay, so we just simple integration, calculate this one, and we get a relation in this. Okay, so 2a by 15 plus b by 4 plus 2c by 3, this is equal to 0. Okay, so if we just multiply by the LCM of these three, then we get 8a plus 15b plus 14c, this is equal to 0. Okay, and similar process for taking this one. Okay, but by taking this second vector, we just get this one, 32a plus 45b plus 18c, this is equal to 0. Okay, multiply by 60. Therefore 4 minus, we just have to calculate, there is 2 equation and 3 unknown. Okay, therefore we can't solve the system in general. Okay, so we have to choose any one of the constant. Okay, so if we first eliminate any one of these 3 constant, then we get, or parameter, we get 44 minus 4 into 3, this gives we eliminate a. Okay, so we get a relation between c and b. Therefore c equal to minus 3b by 16a. Therefore we just write where, since ht, this is equal to a t square plus bt plus c, therefore we just eliminate one constant. Okay, so ht equal to a t square plus bt plus 3b by 16 minus 3b by 16. Now h0 equal to 3b by 16, which is not equal to 0, and it is 0 only when if b equal to 0. But if we get b equal to 0, then from this relation c is also 0 and c is also 0, means a is also 0. Therefore this is a absurd situation. Okay, if a, b, c are all 3 0, therefore there is nothing to do this problem. Okay, so this case is not true. That means the h0, this is b, is not equal to 0. Okay, so d is false option. We clearly say that the d option is what, d option is, I think, h0 equal to 0. So d option is false option. Okay, now we comes to the another options. Now ht equal to we just write this one. Therefore h of minus t is not equal to ht, and h of minus t is not equal to minus of h of minus t. Therefore this is not a even function and this is not a odd function. Therefore a option is also false and b option is also false. Okay, therefore only options remaining is a is false and b is also false. Therefore the remaining option c, we can say obviously, if we discard the remaining 3 options, therefore we can say it obviously that the third option, that is ht equal to 0, has a real solution. Okay, so this is true option. Also you can check, just a minute, also you can check the discriminant, this one is greater than 0, therefore the greater equal to 0, you can say, therefore we can say that the ht function has a real solution. Okay, so you don't need to check out. If we discard 3 options, then we can obviously say that the remaining option is true if the question is right. Okay, so this is the content and this is a to the point discussion on inner product space. I think this video helps you a little bit, or it helps you something to your for your preparations. Okay, so if you like the content, then please give a like to this video, share it with your friends and subscribe to the channel. Thank you friends, see you again in the next video.